Probability and Bayesian Estimation in Python, Complete Beginner Lesson. Welcome! In this hands-on tutorial, you will explore probability, statistics, and Bayesian thinking using Python. No experience is needed. By the end, you will understand concepts like probability, mean, distributions, and you will try beginner-friendly Bayesian estimation with real data. Let us start our journey. Running the cell now. First, we will cover probability basics like coin flips and dice rolls. Let us set up our environment with basic libraries. Warnings are turned off so output stays clean. We import the warnings library. We import convergence warning and value warning from stats models tools. We tell Python to ignore value warnings. We tell Python to ignore convergence warnings. We tell Python to ignore runtime warnings. This comment says we are importing basic libraries for the whole notebook. We import NumPy and call it NP, useful for math and random numbers. We import pandas and call it PD, which lets us organize data in tables. We import matplotlib.pyplot and call it PLT, which lets us make plots. We import Seaborn and call it SNS, which lets us make nice-looking charts. We set the random C to 42 for reproducibility. Running the cell now. This code shows the initial setup for the lesson, where key Python libraries like NumPy, pandas, matplotlib, and Seaborn are imported for data handling and visualization. Notice that warnings are suppressed to keep the output clean as you explore probability and Bayesian estimation. This setup ensures a smooth coding experience without distraction, letting you focus on learning core concepts and analyzing data later on. What is probability? Probability simply means how likely something is to happen. It is always a number between 0, impossible, and 1, certain. Let us try simulating a coin flip. Running the cell now. Let us flip a coin 10 times and see what happens. This is a classic random experiment. This comment says we will simulate a fair coin flip 10 times. We set a random seed of 1 so the results can be repeated. We generate 10 random outcomes of either heads or tails. We print the list of coin flips on the screen. Running the cell now. This output shows the result of simulating 10 coin flips, where each flip can be either heads or tails. Notice that while there isn't an equal number of heads and tails in this small sample, both outcomes appear multiple times, illustrating the idea that each flip is random but still fair with roughly equal chances. This helps us connect the concept of probability to a real example of uncertain but quantifiable events. Try changing size equals 10 to size equals 20 for more flips. Now let us count how many times heads and tails appeared. This comment says we are counting how many times we got heads. We count the number of heads in the outcomes array. We count the number of tails in the outcomes array. We print the totals for both heads and tails. Running the cell now. This output shows the counts of heads and tails from simulating 10 coin flips, where we got 3 heads and 7 tails. Notice that the results are close to what we expect from probability, since heads or tails each have a chance between 0 and 1, but individual simulations can vary. This demonstrates how probability reflects likelihood over many trials, not certainty in just a few flips. If you repeat the flips, the numbers will be slightly different each time because of randomness. Dice rolling, a simple discrete probability. Let us roll a 6-sided die 12 times and see the results. Running the cell now. Rolling a die is another example of probability. Each number from 1 to 6 should have an equal chance. This comment says we are simulating rolling a die 12 times. We set a random seed of 2 so the results can be repeated. We generate 12 random integers between 1 and 6. We print the list of die rolls. Running the cell now. Here, the code simulates rolling a 6-sided die 12 times, showing the exact sequence of outcomes. Notice the range of numbers from 1 to 6, with some values like 1, 3, and 4 appearing multiple times, illustrating the randomness and variability in discrete probability sampling. This output sets the stage for understanding how single trials produce different results and how we can analyze such outcomes statistically. What do you notice? Are some values more common in a small sample? Let us count how often each side came up, just like before. This comment says we are counting the frequency of each die face. We use NumPy-Unique to get each value and how many times it appears. We loop through each value and its count. We print the number and how many times it was rolled. Running the cell now. This output shows how many times each face appeared in 12 rolls of a 6-sided die. Notice that some numbers, like 1, 3, and 4, appeared multiple times, while 5 didn't appear at all, reflecting the randomness in rolling. This counting step helps us understand the distribution of outcomes before analyzing their probabilities. Notice that real randomness may not be perfectly balanced in a small set. Descriptive statistics, mean and standard deviation. Descriptive statistics help you summarize a list of numbers, like your die rolls. Running the cell now. We check what the average, mean, roll was, and how much the results vary, standard deviation. This comment says we are calculating mean and standard deviation. We calculate the mean of the die rolls. We calculate the standard deviation of the die rolls. We print the mean value. We print the standard deviation value. Running the cell now. The output shows the mean and standard deviation of the die rolls, summarizing the data with a typical value and how spread out the rolls are. Notice the mean is close to the expected average of a fair 6-sided die, around 3.5, and the standard deviation indicates moderate variability in the rolls. This connects to the lesson by illustrating how descriptive statistics provide a quick summary of numerical data. Try this with your own list of numbers to get practice. Handling missing data. Missing data happens often in real datasets. Let us see how to spot it and deal with it safely. Running the cell now. Here is an example of a list with a few missing values, called a NaN, which stands for not a number. This comment says we are creating data with a missing value. We create a pandas series with numbers and 2 missing values. We print the word data. We print the data series, which shows the numbers and the NaN gaps. This comment says we are finding missing entries. We check which spots are missing using isNull. We print the words missing values. We print the list of true and false values, showing where data is missing. Running the cell now. Here, the output shows a series with some missing values represented as NaN. The second printout uses .isNull to identify those missing entries, marking them as true. This demonstrates how you can safely detect missing data before deciding how to handle it in your analysis. You will often see missing data when analyzing real information. Let us fill the gaps by replacing each missing value with the mean of the other numbers. This comment says we are filling missing data with the mean. We use fillNo with the mean of the series. We print the words after filling missing values. We print the series again, now with the missing spots filled in. Running the cell now. This output shows the dataset after missing values have been replaced with the column mean, ensuring no NaNs remain. Notice how the previously missing entries are now filled with 5.25, the calculated average, maintaining the data's overall distribution. This step is crucial for safely handling missing data without biasing the results. Try other methods, like filling with 0 or the most common value. Discrete distributions, Bernoulli, binomial, Poisson. Discrete distributions deal with outcomes you can count, successes, arrivals, events. Running the cell now. Let us see 3 basic distributions for counting events. Bernoulli covers single yes-no, binomial adds up several tries, Poisson models rare events per time. We import Bernoulli, binomial, and Poisson from SciPy stats. This comment says Bernoulli models a single coin flip success or failure. We calculate the probability mass function for 0 and 1 with p equals 0.5. We print the Bernoulli probabilities. This comment says binomial models multiple tries with a given probability. We calculate the probability of exactly 6 successes in 10 trials when p equals 0.5. We print the binomial probability for 6 out of 10. This comment says Poisson models rare events. We calculate the probability of 3 events when the average rate is 2. We print the Poisson probability. Running the cell now. This output shows probabilities from 3 key discrete distributions, Bernoulli, binomial, and Poisson. Notice the Bernoulli PMF split evenly at 0.5 for success or failure in a single trial, reflecting a fair coin toss. The binomial value gives the likelihood of exactly 6 successes in 10 trials with p equals 0.5, highlighting how probabilities are distributed over multiple trials, while the Poisson result estimates the chance of 3 events occurring with an average rate of 2, illustrating event count probabilities over time or space. Think about when your life has counted successes or arrivals. Continuous distributions, normal, exponential. Continuous distributions model things that can take on any value in a range, like heights and waiting times. Running the cell now. Let us see what a bell curve looks like and then look at an exponential curve, which measures waiting times. We import normal and exponential from SciPy stats. This comment says we are plotting the normal distribution, also called the bell curve. We create a range of x values from -3 to +3. We calculate the normal probability density for those x values with mean 0 and scale 1. We make a figure 6 by 2 in size. We plot the x values and the normal curve with a label. We set the plot title to normal distribution. We add a legend to the plot. We show the plot. This comment says we are plotting the exponential distribution, which models waiting times. We create a range of x values from 0 to 6. We calculate the exponential probability density for those values with scale 2. We make another figure 6 by 2 in size. We plot the exponential curve in orange with a label. We set the plot title to exponential distribution. We add a legend to the plot. We show the plot. Running the cell now. The first plot shows the classic bell-shaped curve of the normal distribution, centered at 0, illustrating how values cluster around the mean with symmetric tails. The second plot displays the exponential distribution, which starts high and decreases, modeling the probability of waiting times that are more likely to be short but can occasionally be long. Together, these visualizations help you see how continuous distributions represent different types of real-world data. Where do you see bell curves or waiting times in real life? Let us get some real data. The Titanic dataset records what happened to passengers on the famous ship. If not available, we will use the Penguins dataset instead. This comment says we are setting up the Titanic dataset or a fallback. We start a try block. We load the Titanic dataset from Seaborn. We print the shape of the dataset. We print the first few rows of the dataset. We handle the except case if the Titanic dataset is not found. This comment says the fallback will be the Penguins dataset. We load the Penguins dataset from Seaborn. We print a message saying Titanic dataset not found and fallback used. We print the shape of the dataset. We print the first few rows of the fallback dataset. Running the cell now. This output confirms we've successfully loaded the Titanic dataset, which contains 891 rows and 15 columns including key continuous variables like age and fare. Noticing the column types and sample values helps us understand the data structure before modeling continuous distributions such as normal or exponential on variables like passenger ages or ticket fares. This setup ensures we're working with real-world data suitable for exploring how continuous distributions describe measurements with a range of values. Pay attention to columns like survived, sex, and age as we will use them soon. If using penguins, use columns like species, island, sex, and body mass G.